Okay, everybody. So we will go ahead and get started here. What we're going to be covering today is section 5.7 in your book, which is change of variables. I really like this section. It's a lot of fun. Kind of the initial stuff is a little tricky to wrap your head around, but you don't really need much of the theory to actually solve problems. Uh, so what are we going to be doing? I'll give you the idea down here. Um, so basically, we've already done converting Cartesian equations into polar equations in order to make integrals easier, like double integrals. Like if you're integrating over a circle, polar is the way to go, right? And so the idea is, well, what if we're not integrating over circles? Can we do something that would be analogous to simplify in an integral? And the answer, of course, is going to be yes. That's what we're going to be doing. We're going to be changing variables to other variables. Um, so in the section, what we're going to be doing is we're going to talk about transformations, and you're going to determine the image of a transformation. Um, you're going to compute the Jacobian of a transformation. That's a new word. Probably you have not heard that before in any other math class. And then finally, we are going to evaluate double integrals using a change of variables process. Now, actually, doing a lot of this is not that hard, but like I said, we kind of have to slog through a little bit of theory first. So let's go ahead and do that. Let's talk about planar um, transformations. Okay, so let's see. So what is a planar transformation? So a planar transformation is, okay, we'll give it a name too. Transformation T for transformation, is a function, first of all, um, that transforms a region G in one plane into a region R in another plane. So the name planar transformation makes sense, right? Um, they go on a little bit further and say by a change of variables. Both G and R are subsets of R2. Okay, and so here's a little illustration of that. So you've got one plane here, and let's say the variables are u and v. Okay, and there's some region here. So we don't know what the region looks like. It doesn't have to have any particular shape. So let's just say it's kind of like that. Hey, I didn't want an actual box. Let's just say it's like that. Okay, and then let's say that that's a point UV, and this entire region here, that is what we're going to be calling G. So let's shade that in. So the idea is that there's another region in another plane. So this one's going to be the XY plane. And there's going to be a point XY here. And then this shape is just going to be a different shape. So it's just not the same. It just doesn't look the same, right? Uh, and that's our other region. So this is the one that we're going to be calling, oops, R. Okay. And then the transformation is actually just going to be an equation, basically a function that takes a point over here to a point over here. So the transformation basically t does this. So you have the transformation t, you plug in your u and your v, and what comes out is going to be um, x and y. So you could put them in a vector if you want, um, or you could write that maybe like this. So the transformation t could be like x equals one function for u and v, and another function for, I said one function for u and v, one function for x and one function for y, right? So the transformation t does that. And it just takes you from there, from over here to over here. Okay. And so that's just called a transformation. Okay. Now, what we're going to want is our transformations to all have certain properties here. Okay. So we will require our transformation t's to satisfy certain properties. And you'll see why, as soon as we actually get into doing the math, why we need these. So typically what we're going to need is that if we are calling our transformations x equals g of uv, y equals h of uv, we're going to need all of the partial derivatives to exist. So we need all partial derivatives to exist. So specifically, we're talking about, right, you have the function g, you can take the partial with respect to u. You can take the partial with respect to v. Then there's another function h. You can take that partial with respect to u, that partial with respect to v. So all of those are going to need to exist. Um, let's see. Yeah. Okay, what else are we going to need to happen? Well, we're also going to want our function to be what we call one-to-one. So also, let me just say that. We'll want t function from g to r. I don't know why I wrote that there. To be 1 to 1. Okay. And then there's a definition of one to one. You don't have to remember it. So the definition of one to one is a transformation t from g to r, defined as t of uv equals xy, is 1 to 1 if every input uv maps to a single output y, to a unique. No, that's not okay. Let me say that again. Saying that backwards. It's 1 to 1 if I'll use their wording. If no two inputs map to the same output. Okay. Um, there's a lot of ways to say that. You could also say every input maps to a unique output or something like that. But this is how they say it in the book, so we'll just say it this way. And so basically, the idea is that with a function, every input has one output, but what you're not allowing, I'm going to draw this and probably just erase it as soon as I draw it. But like if you have inputs, and you've got some outputs, and then you're just drawing like what the function does, that's fine. That's fine. That's fine. That's not allowed. Okay. Um, Maybe I'll just leave this. Come on. Not allowed. So one to one. So one line from over here, from the inputs to over here to the outputs, everything is going, no line goes to two things over here, no line goes to two things over here. That's one to one. And what a one to one function has is that it's going to be invertible. Okay. That's why we care. So we will need that property. So one to one functions have the property that an inverse exists. So for every one to one t, there is a t inverse such that t of t inverse of whatever variable it is. Oh, I have to think about this. So t went from uv to xy. So t inverse would take in an xy. And if I do it the other way, t inverse of t of uv, that would be uv. Okay, so we're not really like we're not going to be doing anything with inverse functions here, so don't um, worry about it too much. The point is that one-to-one functions have inverses, and that's what's going to allow you to solve for like one variable. Like if you have if you have an equation that says u equals something with x and y, you're going to be able to solve it the other way around and have x equals something of u and v. So it's a property that we need, but we're not going to be dealing with it like in this kind of notation. Okay, so that's a little bit about transformations. What we want to do is we want to, figure out what do transformations do, right? So let's think about what we can do with them first of all. So our first type of problem will be something like this. So um, so let's say dealing with transformations. Okay. So the first thing we can do is we can find an image of a point. That's our first task. So here's an example. So they say, let t be defined by t of uv equals xy, where x equals 4u cubed plus 6v cubed, and y is 9uv. And then they say, find the image under t of -1, 3. So one thing, and then they give you a box like this: t of -1, 3 equals, and then we'll figure it out. Now I do want to point something out that you probably don't notice yet, but when you do notice, initially it's going to make your brain, uh, I don't know, do a thing. So look at this. Right here, this says T of UV equals XY. And um, you know what? Never mind. I thought they were giving us the notation in the backwards form, but they're not. Don't worry about it. Ignore me. Ignore everything I say. Turn off the video, put on YouTube, watch somebody play a video game or whatever it is you watch. I like watching the girl take care of the foxes. Save a Fox, very good channel. Anyway, okay, let's do this. So this is a very simple problem. So we have t is defined by this. Here's a function, and they say find the image under t of -1, 3. And what do we do? Very, very simple. This is the u, this is the v, and we're going to plug them into the formulas. Okay, that's it. So u, v. So all you do is you just say, okay, so the x is going to be 4u cubed, which is -1 cubed plus 6v to the 3, which is 3 to the 3. So you just work that out. And then y is going to be 9uv, which is 9 -1 times 3. So here we have 9 times -1 times 3, so that -27. Up here you have, this is going to be -4. This is going to be 3 to the 3, which, oh no, numbers are so big. And I dropped my Apple Pencil. Life is hard, guys. 9 times 3 to the 3. 6 times 3 to the 3. 162 minus 4. 158. As soon as I find the pencil, we can do this. 158. So this is just 158, comma -27. And that's all you're doing there. So this is not, exactly an ordeal. It's just a function. So you plug the number into the function and you're going to get a result. Okay, so that's the first thing. So we're only going to do one example of that. But the next thing is that the whole point of these transformations is that they transform a region into a region, not just a point, right? Like on our picture, we're supposed to be taking a region over to a region, not just a point to a point. We can do a point to a point, we just did, but what about region to region? And so they're going to give you an entire region and they're going to say what happens. Okay, so we're going to need to find the image of a region. Okay, let's do an example of this. This is also off of the homework. So they say let t uv equals xy be given by x. X is 4u minus 8v. Y is 4u plus 8v. Those are very typical looking equations for this type of problem. And what we need to do is we want to, they make you pick up off a list and they show you the pictures. But what we want to do is we want to find the image under T of the box S equals, so we're plugging in U's and V's, so it's not X and Y here. So S is going to be the set of U and V such that U is in between 0 and 1, and V is in between 0 and 1. It doesn't have to be 0 and 1. It could be 0 and 2, 0 and 3, 5 and 9, whatever it is. They don't have to be 0 and 1 at all. That's not a rule. Okay. So if we think back to our picture, what's going on is this. So in terms of UV, you've got U here, you've got V here, and then we just have a very simple box here. This is 0, 1. Um, I just erased everything. So we're looking at a box like this, 0 to 1, 0 to 1. Okay, and then what we're doing is we're going to apply T, and what does it look like? Okay, um, and I'll draw a set of axes here, but we might have to change them because we don't know what this actually looks like. Okay, so what we want to know is what happens to the box 0 to 1. Okay, so um, one note that I have is this. Well, no, you know what? Let's not do that. Let's do this first. First of all, the easiest way to get started with a problem like this is to look at where the corners end up, because you have 4 corners here. You have a corner at 0, 1. You have a corner at 1, 1. You have a corner at 1, 0. And you have a corner at 0, 0. So easiest thing is just going to be figure out where the 4 corners go. So this is basically like doing the last problem 4 times, right? Okay. So we've got our X and our Y here, right? So if I just duplicate this, I come down here, then we can just check each point. So like, where does 0, 0 go, right? So 0, 0, actually I should, to keep track of what's U and what's V, we're starting with UV equals 0, 0. So where does that go? Well, you plug that into the equations, right? So X is going to be 4, 0 minus 8, 0. Y is going to be 4, 0 plus 8, 0. So you end up with 0, 0, right? So we end up with xy equals 0, 0. So it turns out that, over here, you are going to have 0, 0. Okay? But there's 3 other points. Where do they go? So the next one we could do would be, let's say UV equals, we can do any of them. Let's do this one. Oops, because I see it. Let's do this one because I see it on the screen, 1 to 0. So where does 1, 0 go? Well, we're going to plug that in now. So X is going to be 4 times 1 minus 8 times 0. That's going to be 4. Y is going to be 4 times 1 plus 8 times 0. That's going to be 4. Right? So we go to xy equals 4, 4. So 1, 2, 3, 4. 1, 2, 3, 4. There. All right. So we're making a start here. Oh, by the way, actually, let me erase this. We don't actually know that there's a straight line there. There is, but we don't actually know that it's a straight line. And so I do want to make a comment about that before we get to that point. All right, what's the next point? I think we have one at 1, 1, right? That was another corner. Yep, 1, 1 and a 0, 1. Let's just do 1, 1. So we have x equals 4 times 1 minus 8 times 1. That's going to be negative 4. And then y is going to be 4 times 1 plus 8 times 1. Ooh, that's going to be 12. 412. Interesting. I did not leave myself any room to do that, right? So let's change the axes here. Let's just let's go like 4, 8, 12, right? We're going to count by um, twos here. 4, 8, 12. Okay. So now we got 0, 0, 4, 4. And then the point we just came up with is 4, negative 412. Really? Yeah, okay. Negative 412. Negative 412. Way up here. All right. Last point. UV is, what was it? 0, 1. So that's going to be x is 4 times 0 minus 8 times 1. That's going to be negative 8. Y is going to be 4 times 0 plus 8 times 1, which is going to be 8. 8. 8. I feel like I've ruined this. What did I screw up here? Am I missing a negative? Oh, okay. Negative 8, 8. Okay. I was like, that just feels like the wrong point. XY is negative 8, 8. Okay. Like I thought it was over here, and I was like, well, that doesn't look right. But no, negative. I hate how it goes into eraser mode without me noticing. Okay, so there you go. So again, the point that I want to make here is this is actually what the region looks like. It's a rectangle, but they don't have to be rectangles. It could be curved edges like this. Like you just don't know. Okay. Now, when I say you just don't know, I mean, I actually do know they're straight edges. But the way that you would figure out that the lines are straight is actually a little bit tricky. Now, on the homework, they're not making you deal with those curved edges here. So just knowing these 4 points would be enough to get the right answer because it is a rectangle. Okay. But that's why I call this step 1, figure out where the 4 corners go. Okay. Step 2 would be if you wanted to figure out what kind of curve connects the points. So I'll say if needed, you don't on the homework. Figure out what kind of curve you have for the edges. What kind of edge curve you get for the sides. All right, so here's how you would do that. So like, for example, on the original, I'm going to finish that sentence someday. Yeah. So like on the original, you've got like something like this, like 0, 0 up to 0, 1, right? So if you take a piece on the UV plane, right, you could actually parameterize that curve, right? So you can parameterize. I know I'm giving you flashbacks to like the optimization section, but you don't really need to do this very often. In fact, not at all on the homework. So you can parameterize um, one of the sides, like the one that I highlighted, right? Like this line segment from 0, 0 to 1, 1. Um, so for example, the one that I just showed there, 0, 0 to 1, 1, you could say that that parameterization would be not x because this is the UV plane. U is just constantly 0, right? On this piece right here. Because like U is 0 and V is V. right? For that, the piece shown. Okay. Then what you can do is you can plug that into your transformation. So your transformation was x was, what was it? 4u was this, right? 4u minus 8v, and then y was 4u plus 8v, right? So you plug that into your transformation, you get x is 4 times 0 minus 8v, and you end up with y is 4 times 0 plus 8v, right? Which would tell you that um, x is negative 8v and y is positive 8v, right? Then what you can do is on these, you can solve for v and set these equal to each other. So on the first one, right, if you had x equals negative 8v, then that is negative x over 8 equals v. And if y is positive 8v, then that is y over 8 equals v. And then those two things, now that they are both equal to v, you can set them equal to each other and say that negative x over 8 equals y over 8. Or if you now multiply both sides by 8, negative x equals y. Okay? And where is that? Well, let me show you. Let's go way back up here. Let me get this picture. So this is the picture that we had before, right? And if you plot this curve, y equals, in this case, negative x, um, that is this line, right? And this section must be the section that corresponds to this section. So you could do that from each of the four sides, and that's how you would know if the sides were curved or straight or whatever, right? Because this is a straight line. Um, so on this problem, the sides are straight, but not always. Okay. Now, again, this was completely unnecessary to do. You did not need to actually figure out that this side was going to be a straight line. You definitely don't need to figure out that this is a straight line and this is a straight line and this is a straight line. But if you wanted to, feel free to do this process for all of the other sides and you could figure that out. Um, if you did, then once you had that worked out, then you can go up here and say that we know exactly what this looks like now. It's a rectangle. Okay, but if you know where the corners are, you can do the homework. Doesn't matter what the sides look like. Okay, so hopefully that made some kind of sense. What we did there, even if it was kind of off on a tangent a little bit. Okay. So we did that. So that's fun. Um, okay. Let us now let's get into talking about Jacobians. And I'm going to be a little bit hand wavy during some of this work um, because it's tedious and confusing. Uh, so not the most fun thing to do right here. But once we're done with it, then we just need the result that we're going to derive here. Okay. So we're going to be doing integrals. Okay. Integrals. Right? And because we're going to be doing integrals, we're going to need to know what the area element dA is. So what dA is for a transformation. For example, for the polar coordinates, right? We have one. We just gave it to you for polar coordinates. dA was r dr d theta. Okay, but for every transformation has its own thing, right? So every transformation has its own dA. Okay, so that's why we're doing this. And now let's get started. Okay, so we're going to be doing this because we're going to be doing integrals in the future, right? So here's how we're going to do it. Um, Consider a box with dimensions delta U and delta V on the UV plane. So what we're looking at is some little box. Make straight lines. Come on, you can do it. Okay. So you have a little box, and this is in the UV plane. So this is U, this is V, and then we've got this little box here. Okay. Now this little box has dimensions. As I said, you're going to have a delta U down here, and this side is going to be a delta V. Okay. Now what we need to know is what's going to happen to that box when we apply the transformation. Okay. Um, so here, apply the transformation T. And as we said, it's not guaranteed to have straight sides. They can just be whatever they are. So let's suppose it looks like um, this. Okay. And so we know that that kind of thing can happen. Oops. We know that this kind of thing can happen. And that's what's going on here. Okay. Um, so it's not a thing now. So what we have to do is we have to figure out what the area is over here in the XY plane. That's what we got to figure out. And so this is where I'm going to be a little bit hand wavy. So the first thing is this shape here is not a parallelogram. So let me note that. Um, this is not showing a parallelogram because the sides are not straight. But um, the smaller it is, the straighter the sides will look. That's kind of like how, um, if you look at the earth is round. But if you look at the ground, like a little piece of the ground looks flat, basically, right? That's because if you only look at a little piece, it looks straight enough. Okay, so the smaller it is, the straighter the sides will look. Um, so instead of the picture that I drew, let's look at this picture. Well, couldn't even draw a straight line there. So let's try to draw kind of the same looking shape here. I want to draw the sides not like straight up and down as well. So I'm going to draw that a little bit tilted. If it will let me draw it a little bit tilted. Okay. Okay, close enough. Okay, so this is in the XY plane still. Okay, I'm just saying pretend it does look like a parallelogram. All right, then what you would need to do is you would want to know how long the sides are on this parallelogram. So on that second picture, second XY plane, I should say, not the second picture. All right, and this is where I'm going to be a little bit hand wavy. Okay, so think about the example that we just did. So when we were looking like up here, there was a way that you could, for an individual side, like this side right here, you can do some math, and you could figure out where that side goes, right here. Um, in principle, you could do the same thing here. Like if you take a side here and it goes here, if you know this length, you should be able to figure out this length. Okay. And so what they do is something like this, because I'm not going to do it properly. I'm not going to do it in detail. Um, so let's say you have this side right here. Okay. Now on this side, just like the example that we did, what you have is u is a constant there, right? Because, like, let's say that's u0. Because along this entire line, u is a constant. However, v varies in this section right here. So that's a little piece of a curve that's u, some constant u naught, comma v over here. And its length is delta v. Well, over here, if we apply the transformation, then what you would do is you would end up with this section of the curve. I mean, maybe. I mean, could be a different section of the curve, but let's say it's that section. Okay. And what we want to know is what is this length in relation to the previous length? And it's actually related to the derivatives of the transformation, which I didn't write. But so if we apply the transformation here, let's say the transformation is given by this. T of uv is ordered pair. There's a function g, and then there's a function h. So just the same words that we've said before, but that's the transformation. T of uv equals g comma h. Okay, well, it turns out that the direction that we have here, and actually the length that I drew, is going to be this. So this as a vector is going to be um, the x component here, which is g of uv, take the derivative with respect to u. The y component here, take the derivative with respect to u, which is going to be hu. And then obviously the longer this side is, right? If you make this twice as long, wouldn't that make this twice as long? Yes, it would. So the way this is related to this is also with a like this, g of u, and then whatever that delta v is. Wait, I lied. I lied. I lied. I lied. I lied. Let me start over here. Um, if u is constant, v is the variable. So you would take the derivative of this with respect to v, and you would take the derivative of this with respect to v for this side. So this would be actually the derivative of g with respect to v, and then times the delta v, and then the derivative of h with respect to v, and then the delta v, which delta v, and that's what that side would be. Okay, and then if you do the other side, like this side, that one would be the derivative of g with respect to u, delta u, derivative of h with respect to u, delta u. Okay, and so I didn't do the math to derive that, but that's what it would be. And the reason you only have the derivative with respect to v over here and the derivative of u with respect to u over here is because there is no derivative with respect to the other variable, because on this part only v changes, and on this part only u changes. Okay, so again, that's the part that I'm not deriving. I'm just saying it. These are what these two vectors are in relation to this right here. Okay, now having done that, once you have that parallelogram, what we need to do is figure out the area. The area of the rectangle is obviously delta v times delta u, right? Length times width. But this is not a rectangle. This is a parallelogram. So we need the area of a parallelogram. So we need the area of the parallelogram shown. Okay, now you have to remember how to do that. So just recall back to the beginning of the semester that the area of a parallelogram is given by magnitude of like a cross b, where those are the vectors that determine the parallelogram, right? So for us, what we're going to do is we're going to take our parallelogram vectors, right? So for us, the vectors are, so one of them was ru delta u, comma r, no, ru, not sorry, I said ru, I don't want ru, I want uh, gu, yeah, gu delta u, hu delta u. And then what we have to do is pad this with a 0, because in order to do a cross product, we need a three-dimensional vector. And the other one would be, what was it, gv delta v, hv delta v. And then again, just stick a 0 on the end here. Okay. Then the other thing they do is they change the name of the variables um, on you. So I'm going to do that right now as well. So they also, at this time in the book, change some names around. So instead of using um, like x equals g of uv, y equals h of uv, they just switch it to about x just x of uv and y equals y of uv. I mean, we can name them whatever we want, right? So why not use x for x and y for y instead of g and h? Okay, so we actually have to do this. So for the area of the parallelogram, we want this. Um, the magnitude of, we want xu delta u, yu delta u, 0 cross yv delta v, wait, sorry, xv delta v, yv delta v, comma 0. Okay, and that's the area. So this is our delta A. Okay, now they take that, you have to calculate that. So you have to do this cross product. We're already taking a long time just for this derivation, right? Which we don't really want to do. So let's just go on Wolfram Alpha and make Wolfram Alpha do the cross product here. Actually, can I don't know. I'm trying to think about how to write this in Wolfram. I'm just going to do this. Okay. So I'm just going to say pretend my vectors are AB0 and CD0. Okay. So I'm going to do cross product of um, AB0, comma CD0. I got an extra 0 on there. Dang it. I was trying to do parentheses. Oh, well, now I have unbalanced parentheses. Okay, it fixed it. Okay. All right. So it did this. Where is it? Okay. Result 0, 0 minus BC plus AD. So if I just kind of copy that, right? So like if I'm just pretending A, B, C, D, that's what I was doing. And we just copy our answer, then this is going to be, we still have to do the magnitude, but the A is XU delta U. The D, I didn't write it, D, D. The D is YV delta V minus B, which is YU delta U, C, which is XV delta V. And then we want the, oh, actually, that is the magnitude. What am I doing? Sorry. Let me back this up. Copy the wrong thing into the wrong place. The actual vector that you get here is 0, 0, and then negative BC, which is negative YU delta U, XV delta V, plus AD, which is XU delta U, YV delta V. Okay. And then when you do that, then that's your result. Okay. So let's just back this up. So in order to find the area of the parallelogram, you have to know the length of the sides, which we just I gave you. Then you have to do this cross product, which you get this. Then after you do the cross product, you're doing the magnitude of the cross product. Yes. And this is the result. Okay. So it looks pretty complicated, but you can write it this way. We can summarize it a little better. How about parentheses xu yv minus yu xv, and then you can stick the delta u delta v on the end. Okay. Or even, this is not any different. This is just writing things in alternate notation. Xu, that's the partial of x with respect to u, and then partial of y with respect to v minus partial y with respect to u, partial x with respect to v, delta u delta v. Okay. So there is a thing. Okay. Now, with all of this done, we just want this result. So the thing that's in the parentheses there is just what we call the Jacobian. So then this is just definition. The Jacobian of the C1 transformation. I'll explain that in a second. T of uv equals g of uv h of uv is denoted j of uv and is defined as, so j of uv, they use this symbol. So this is just notation here. So you don't have to pay any attention to that middle one that I just wrote. And, but it turns out that it's this dx du dy du dx dv dy dv, and oops, that seems complicated, but that determinant that I just wrote there is just, if you remember how determinants work, right? Like you go those two minus those two. So it's partial x with respect to u, partial y with respect to v. That's this diagonal. And then minus this diagonal, which is delta x, not delta, dx dv dy du. And that's just what we wrote up here. That's this. You can't see that. That's this. Okay, so this is the Jacobian. But it doesn't matter. Like, we did all this math to get to this point, and then this thing here, we just give it a name. This thing is called the Jacobian. That's what this says. C1 means the first derivatives are continuous. If it was C2, that would be the second derivatives are continuous, and so on. So the Jacobian of the C1 transformation is denoted JUV and is this. Okay, so that's just that's just the definition of the Jacobian. Now, why do we care? The reason we care is because of this. So we can write now that on that parallelogram, that delta A was approximately equal to, I say approximately equal to Because remember, way back here, um, the actual thing is not a parallelogram. It's got curved sides, theoretically. Um, the If we pretend it has straight sides, then it's a parallelogram, and we calculated the area of that parallelogram to be this. So they say delta A is approximately equal to the Jacobian, um, and then delta U, delta V. Okay. Um, so yes, that is what we're doing. Um, so the first thing you're going to do with the Jacobians is they're just going to make you calculate a Jacobian. So let me do that because there is actually a trick to it. Let me just say what we're doing actually. So computing the Jacobian of a transformation. Okay, so I'll write like a note or two. So first thing is usually um, wait, yeah, it's okay. So sometimes you have equations given as x is a function of uv, y is a function of uv. That's what you want. Okay. But um, if you have an integral, a lot of times you're going to have it the other way around first. So, um, but if you came up with the transformation yourself, you probably have it u equals something, v equals something. So you might have like u is some other function. So I'm just gonna like give it a name. Like I don't know what variable to use. I'll use s. You might have like u is s of xy, and then v would be like t of xy. So you see the difference, right? Like here, you have this is solved for x and for y, and this is solved for u and for v. And if that's the case, you're going to have to solve for x and y somehow. Okay. Um, if you have the second thing, have to solve for uh, x and y somehow first, and that could be some work. Lots of exclamation points because if you forget to do it, you can't do the problem. Okay. So that's just a note that I wanted to talk about first. Um, Having said that, actually finding the Jacobian, if they give you your equations in the correct form, it's not going to be there's not going to be anything to it. So do not stress too much here. So like here's an example. Again, this is going to be straight off the homework. Um, Oh, that was number one, right? I said, so that was number one. And then number two, after you have it in the correct form, uh, if you do have x equals a function of u and v, y equals a function of u and v, then just compute. You need x, u, x, v, y, u, y, v, and you plug those into the Jacobian formula here. J of uv was this determinant. So it was xu, what was it? Xu, xu, yu, xv, yv. If you like switch the order of these, then you get the same answer, but kind of wrong. So xy, xy, x, oops, back up, xy, xy, u, v, v, u, v, v. So that's just the other notation there. Okay, so no big deal. Let's do it. Let's do an example, and you'll see that it's actually far easier to do than what we've just talked about. So they say let t be t of uv equals xy, where x equals 2u squared plus 5v squared, y equals negative 4uv. Oh, I thought I was on a Jacobian question and I'm not. Oh, well, we'll find the Jacobian anyway. Um, I'm just going to say find the Jacobian, JUV. This is not the question it was actually a completely different question than I thought it was. I was thought we were going to find a Jacobian. All right, let's do it. So, your first step is just going to be to find all those partial derivatives, right? So we're going to find xu, or you could write them, the other notation, but xu, xv, yu, yv. So just all the partials. So xu is going to be partial of x with respect to u. That's going to be 4u. Xv is going to be the partial of x with respect to v. That's going to be 10v. And then you've got yu. That's going to be the partial of y with respect to u. So we're taking the derivative here. Oops. So partial derivative here with respect to u is going to be negative 4v. And then yv is going to be negative 4u. Okay, so you just find your partials, and then you use your Jacobian formula. So j of uv is going to be, what is it? xu, xv, yu, yv. Is that correct? Nope. I knew I was going to get it backwards at some point. Xu, yu, xv, yv. It's actually the exact order that I put them there. So you put them in the right place. So you have 4u, negative 4v, 10v, negative 4u. And here, this is just the determinant here. So you just multiply these out, right? So you just go these two multiplied together. So 4u times negative 4u is going to be negative 16u squared. And then minus these two squared. So, or not these two squared, just those two multiplied. So negative 40v squared. So overall, you get negative 16u squared minus a minus, which is a plus, 40v squared. And that would be my Jacobian. Yeah. Okay, we'll do one more of these computing the Jacobian, and then we'll do some integrals. So, one more example. I'm just going to say find the Jacobian of T of uv equals negative 8u e to the 8v, negative 8, negative e to the negative 8v. And that is, they say, xy. So this is how they write it in the homework, and we're finding the Jacobian. Um, so all this is saying is x, right? X here is x here. So this is negative 8u e to the 8v, and y is negative 8 e to the negative 8v. So again, if we're going to do this, this is not going to be super hard. We're just going to find the partials, right? Very straightforward. So we need x, partial x with respect to u. So this is a v. So when we take the derivative with u, there's only one u here. So there's no product rule or anything. It's just going to be negative 8 e to the 8v. We're going to need partial of x with respect to v. So that's going to be, if we take the partial of x with respect to v, it's going to be negative 8 u e to the 8v. And then the chain rule is going to make me multiply by the derivative of 8v, which is 8. Now do the same thing for y. Yu is going to be the derivative of y with respect to u. There is no u, so that's 0. And then you need partial of y with respect to v. There is a v that's going to be negative 8 e to the negative 8v times the derivative of negative 8v, which is negative 8. Okay, so you find your partials. Once you find your partials, we're going to use our formula again. So find Jacobian. So j of uv is going to be this determinant, and I wrote them in the right order again. So negative 8 e to the 8v, 0. Wait, did I put them in the wrong place? Yeah. Wait, hold on. Did I put them in the wrong place there? Whoa, 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 whoa. Give me a second here. Oh, I did. Hold on. I just wrote it wrong like a bunch of times in a row. It's not like wrong in a way that matters. Don't worry. Let's go back up and fix this. This is the one that goes in the upper left. This goes down here. This goes here. Now, what's that change over here? Nothing. Okay. So the top row is x. The bottom row is y. Okay. Sorry about that. I don't know why I have like a brain fart on this, like a mental block, but I forget that over and over and over. So top row x, bottom row y. Top row x, bottom row y. It does not change the answers because it doesn't change the answers, which means that technically the formula that I wrote is still 100% correct. So I didn't technically make a mistake. What I did was I wrote the formula, a different formula than the book, even though it's literally the same thing. So it's not an issue. Okay, but if we wanted to match the books, this is what we'll do. All the answers were right. Okay, so the top row is x is for x. So we have xu, xv. Actually, let's multiply let's multiply these out too. 8 times 8 is 64. So negative 64u e to the 8v. And then bottom row is for y, yu, and then negative 64 e to the negative 8v. Okay, so you find the Jacobian. We're going to multiply these, right? So these two minus these two. So we have, it's going to be 8 times 64 e to the 8v, e to the negative 8v. For these two, I took care of the minuses already, and then minus these two. So minus 0, negative 64u e to the 8v. So the second one is 0. This one here, 8 times 64, that feels like 512. E to the, when you multiply these, you add the exponent. So it's actually 8v minus 8v, which is 0. So you end up with 512 e to the 0, which is just 512. And that's your Jacobian. Okay, so that is how you calculate Jacobians. Okay, so then now what we want to do is actually calculate integrals now that we're over an hour into this. So computing integrals with change of variables. All right, so I'm not going to do like derivation with a Riemann sum or anything. We've seen that too many times. What I am going to do is I'm going to say this. So I'm just going to say, recall what we just did, that the delta A for the transformation was, what was it? It was, well, it was the Jacobian, right? So it was the Jacobian and then dA. Okay, we had that. So what's going to happen is this. So here's our definition, and this is what we'll use. So let T of UV equal XY, where X is a function of U and V, and Y is also a function of U and V. So this is all the same stuff. It needs to be 1-to-1. R. No. Is. No. B. Let this be a 1-to-1. A 1-to-1 function with continuous, a 1-to-1 C1 function. Okay. With a non-zero Jacobian on a region S in the UV plane that maps S onto R in the XY plane. All right. So let me just mention a couple things here. So we already said that we're going to want these functions to be 1-to-1, and they need to have continuous partial derivatives. They need to have continuous partial derivatives because we need to be able to do these Jacobians, which requires derivatives. Okay. Also, it says that we want the Jacobian to be non-zero. Okay. So that's just a requirement. They didn't explain why. But I think that will keep, I think what that will do is it will keep an area in the UV plane from mapping onto a point in the XY plane. I'm not sure, but something like that. So this is just requirements that you need your transformation to have in order to make this work out. Okay. So then if F of xy is continuous on R. Then finally, we can get to the actual definition we care about. The double integral over R of f of xy dA. So that's the integral you start with. You're going to change it into an integral over S. And what you're going to have to do is you're going to plug in what x is in terms of u and v, what y is in terms of u and v, and then your dA turns into the Jacobian uh, du dv. Okay, give me 1 second here to check on something. Okay, yeah, they actually, so this is actually going to be the absolute value of the Jacobian as well. Okay, which makes sense. We're trying to figure out an area. We don't want like a negative area. Okay, so, uh, right. So that's the formula. So that is how we're going to calculate these. Now, just knowing that is not really enough. Like I wrote that all down, but that's not how you're going to do integrals. Okay. So there's like a set of steps that we're going to follow. Um, so let me write our problem solving strategy down and then we will try some. Okay. Um, okay. So the first thing you're going to do is you're going to like you start with an integral, okay? So you're given the integral in terms of x and y. You are given double integral over r f of x y. I'll write dx dy, but I could write dA, but I want to make it clear that we're talking x and y. Okay, so you're given that. So first thing you're going to do is you're going to sketch the region of integration in the xy plane. Okay. When you write, when you sketch the region, you're going to find equations for the boundary. So for the curves on the edge. So find equations for the curves on the edge. Okay. Um, then what you're going to do is you're going to choose your transformations. Okay. So you're going to find your transformations. Often you'll start with u equals something, y equals something. No, u and v. But then you will have to solve it the other way. The other way around. You will have to figure out x is a function of uv and y is a function of uv. Right. So you might start with u and v, but you're going to end up with x and y. You'll have to figure it out. Otherwise, the problem cannot proceed. After you do that, you're you're going to figure out what your new limits of integration are. That's going to be really easy typically. Because we're setting up an integral, so we'll need to know the limits of integration. You're going to need that Jacobian. J of uv. Um, you're going to figure out what f is when you plug in your functions for x and for y. We're replacing the x's and y's with u's and v's. That's what we're saying there. And then finally, you're going to, set up the integral. Integral over s of f of g u, no, g of uv, h of uv, absolute value of the Jacobian, and then the dA. Okay, mostly I'm writing this in case you like forget a step. You can come back and look at that, and then maybe you realize that you didn't do something. Now, none of that really makes any sense until you solve problems. Okay, so when you first solve problems, you're not going to have to do all of this at the same time. Okay, often what they're going to do is they're going to tell you the substitution to use. So let me see if I can find one in the homework where they just straight up tell you what transformation to use. Just looking. Oh, come on, just give me one. Okay, yeah, that'll work. Will that work? Yeah, okay. So here's an example. Okay, so this is our first example. Okay, so first of all, they're giving me a picture. And the picture goes, let's call that 1, let's call that 2, let's call that 1, let's call that 2. No, let's call that, okay, 1, -1, +1, 1, 2. Okay, so what is going yeah. So we got a point here, 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 we got a point. So we go connect the dots. They give us this region, they show us it, they shade it. Okay, so we have this region. And this region they're going to tell us is R, R. Okay, and then they're going to say, use the transformation um, oh, this is a little bit different in the book. It's a little bit annoying actually. U equals y minus x, v equals x plus y to evaluate the double integral over r of e to the x plus y dA. So let's just look at this, make sure it's clear. We're trying to integrate this integral over this r And these are the transformations they say to use. Now, the reason you would want to use a change of variables here is because if you don't use a change of variables, then what you have to do is do two integrals, because the top curve here is different than the top curve here. Sorry, the top curve on the left half is different than the top curve on the right half. So you'd have to do one integral for the left part, one integral for the right part. And if you switch the order of integration, then you would still have to do two integrals, because the left curve and the right curve here are different than the left curve and the right curve down here. So if you don't change the variables, you would have to do two integrals. And that's why you might want to do a change of variables. Okay, so we're going to do a change of variables because they told us to. Okay, what else can I say about this before we get started? The other thing is, you'll notice that it says use the transformation and it's u equals v equals. That's exactly what I was talking about when I said um, often you'll start with u equals something, v equals something. Okay, so that's what happened. Uh, Also, they do label the sides of this, so I will label the sides of this as well. So they say one line is y equals x, that's down here. Um, one line is negative x plus 2. I think that's this one. Y equals negative x plus 2. One of them is y equals positive x plus 2. That must be this one. And then one of them is y equals negative x. That must be this one. Okay. So let's go ahead and get started here. So first of all, I want to go over why you would use these substitutions in the first place, why that transformation. So this is just an explanation. Um, um, this is just like a why would we be using the transformation they say. And this will make it easier in a little bit when we try to set up our own. So here's why. So the curves that they gave us are the following. So we just have to write them all down. So we had y equals x, y equals negative x, y equals x plus 2, y equals negative x plus 2, right? But if you put all the variables on the left and constants on the right, look what happens. Write all of them this way. Variables equals constant, right? So just variables on the left, constant on the right. Then what they are is like y equals x would just be, um, if you move the x over to the left, it would be y minus x equals 0, right? And if you have y equals negative x, that would be y plus x equals 0, right? And then the third one was y equals x plus 2. If you put the x over, it would be y minus x equals 2. And then if you put the fourth one, y equals negative x plus 2, move the x over, you would have y plus x equals 2. Okay. And then what you realize if you write them all this way, you see that they come in pairs. They are either y minus x equals constant, or y plus x equals constant, right? Y minus x, y plus x, y minus x, y plus x. So you should notice that right away, and then 0, 0, 2, 2. And then that tells you that you want to use one of these for u and one of them for v. And so they used, which way did they do it? U was the first one. So they suggest y minus x should be u and y plus x should be v. Okay, so that's actually how you come up with the u and the v in the first place if they don't tell you it like they told you it here. Okay, so that's just nothing you have to do. That's just where they came up with it. All right, so let's go down this list. So sketch R in the xy plane. Sure. Find equations for the curves on the edge. They gave them to us. Find your transformation. Often you'll start with u equals something, v equals something. Okay, but you will have to figure out x equals y equals. So this is where we are. Okay, so we have u equals y minus x and v equals y plus x. We need to do algebra to come up with x equals a function of x and y, no, u and v, and y is some other function of u and v. Okay, it's not as hard as you think. So, well, I don't know how hard you think it is, but we have u equals x plus y, right? So let's call that equation 1. And equation 2 is v equals x minus y. So if you just do, this is like solving an equation, right? So like if you just do, let's just subtract 1 and 2, right? So if you do u, or actually just add, that's easier. Add u plus 2. So if you do like equation 1 plus equation 2, you have u equals x plus y, and then we add it to v equals x minus y, right? Plus, what's the result? On the left, you get u plus v, and on the right, you get x plus x, which is 2x, and you get y plus negative y, which is 0. So you end up with this, x equals u plus v. Or x is u plus v over 2. That's one of the things you need, right? That's what we mean when we say x is a function of u and v. X, u and v. All right, now we can subtract. Subtract 1 minus 2. What will happen there? So we'll do u equals x plus y minus v equals x minus y. So we end up with u minus v. And then here we end up with x minus x, gone. Y minus minus y, which is going to be negative 2y. Or divide both sides by negative 2, we're going to get y equals u minus v over negative 2, or v minus u over 2. Okay, so we have that. So that's what I'm talking about when I say that if they give you equations in terms of u and v, you have to come up with x and y. And it's just a little bit of algebra. It's generally not going to be hard, but some things are hard, some things are easy. All right, figure out what the limits of integration are in the UV plane. So limits of integration. So recall the equations of the line. So the boundary or the curves on the edge. So the curves were, we wrote them all down. I'm going to copy them here. So we don't want this form. We want this form. Okay. So those are your curves along the edge. And what you do is just figure these out here. You have y minus x and y minus x, right? And also you have y plus x and y plus x. Well, what is y plus x, right? Y plus x is u, or x plus y is u. That's u, that's u. And the other one, y minus x, was v and v. So what that tells me is if you do that replacement, the top equation is actually v equals 0. The next one is u equals 0. The next one is v equals 2. And the next one is u equals 2, right? So these are the boundary in u and v. So what that's actually telling you is that in the UV plane, what you have going on is this is your region. Just 0 to 2, 0 to 2, right? U equals 0 to u equals 2, v equals 0 to v equals 2. And that's why you write it this way to figure out the u and the v, because then this will just be obvious. Okay? So what do we do then? We should just be able to, oh, we need the Jacobian. We haven't done the Jacobian yet. My God, we haven't done anything. All right. Jacobian. So you need the x, right? You need it in the x form and the y form in order to do the Jacobian. So I'm going to write them. So x is 1/2 u plus 1/2 v, and y is 1/2 v minus 1/2 u. Okay, so your partials are xu is going to be 1/2. Xv is going to be also 1/2. Yu is going to be negative 1/2. And yv is going to be positive 1/2. So the Jacobian is, I remember top row is x now, 1/2, 1/2. Bottom row is y, negative 1/2, positive 1/2. You work this out, it's just 1/2, 1/2 minus negative 1/2, 1/2. So it's actually a quarter plus a quarter, which is a half. So sometimes the Jacobian is just a constant, sometimes it's not. Okay. Um, with that said, we should be able to set up our integral now. I hope. Yeah, okay, fine. So I'm just gonna combine steps 5 and 6 here. I don't know why I called them separate steps anyway. All right, let's just set up the integral. Okay, so your integral, we're doing the integral of f of x, y. Okay, dA was actually, they told us it was e to the x plus y. I already forgot it, but I just looked at it. It was e to the x plus y dA, right? So what we have to do is this. So our integral, first of all, we have bounds for u and v. They are 0 and 2 and 0 and 2. So what we call it S, I guess, UV, such that U is between 0 and 2, V is between 0 and 2. Okay. So we know what we're going to do is we're going to have bounds for U and V are going to be 0 and 2. Now your E, it's X plus Y, but you need X plus Y in terms of they are right here, right? So let's move them down so we can look at them. So the U is actually 1/2 U plus 1/2 V, plus the Y is 1/2 V minus 1/2 U. So you have to plug those in to your X and your Y. Right? And then you have your Jacobian, absolute value of the Jacobian, and then you have your dA. So when we do this, it's going to be 0 to 2, 0 to 2, e to the, you have to work this out. We have 1/2 u minus 1/2 u, they cancel. 1/2 v plus 1/2 v, that's actually just a v. Then you have your Jacobian. Jacobian was 1/2. We stick it in absolute value. And then you have your dA, which, it doesn't matter which one we do. So also like dv dx. They're both 0 to 2, right? So that's the integral that you actually have to do now. So do you see how the integral becomes very simple? 0 to 2, 0 to 2, 1/2 e to the v dv. I wrote dx, but dv du. U. Okay, so let's just finish that. So let's just integrate. So 0 to 2, I'm just going to integrate this. So antiderivative of 1/2 e to the v, 1/2 e to the v, 0 to 2, du. So we have integral from 0 to 2, 1/2 e to the 2 minus 1/2 e to the 0, du. 1/2 e to the 2, this is just going to be minus 1/2, isn't it? Du. So integrate. So we have 1/2 e to the 2 minus 1/2 u, 0 to 2, right? This is just a constant now. This is just a constant now. This whole thing is a constant. So we put in a 2 for the u. So we're going to get 1/2 e to the 2 minus 1/2 2 minus 1/2 e to the 2 minus 1/2 0. So overall, we're just going to have these things multiplied out. It's going to be e to the 2 minus 1. So I think that's right. Point is that the integral was easy, even if I made a mistake there. Okay, so that was fine, but like I said, that was harder than I intended for it to be. Okay. Um, so I'm going to find an integral from the actual homework because the actual homework is easier generally. Okay. So this is from the actual homework. They say use x equals u, 3y equals v. Okay, that's not going to be too hard. To set up um, the integral, double integral over r, x squared plus 9y squared to the 1/2 dA over r Actually, this is kind of a little bit harder than I thought it was going to be now that I'm writing it out here. But that's fine. We're smart. We can do it, right? Okay. So R is here. The only thing that makes this hard is it's sort of just awkwardly written. So they give you this integral, they tell you this is R, and then they say we want to set up the integral, but then they say that we have to write our answer in polar coordinates, which is weird. Um, yeah, which is weird. Okay, so then they say give answer in polar coordinates. Weird. Like I said, it's weird. So here's what we're going to do first. We can do kind of the stuff in different orders here, right? So I'm just going to not do everything in the order that I had in the previous problem. So let's just look at this. First, we have the double integral over r, x squared plus 9y squared to the 1/2 dA. Sure. Okay. Now they told us what to use for the x and for the v actually, right? They said x equals u, 3y equals v. So they said x equals u, 3y equals v, right? You can substitute that into your integral pretty easily, right? Like, first of all, the second one here, just move the 3 over, would say y equals v over 3. Okay, so I'm just going to write out the integrand. So the integral, the grand would be like this. So we have integral over r. If you substitute those in, right, it's going to be u squared plus 9y, which is v over 3 squared, 1/2 dA, whatever dA is, we don't know yet. U squared plus 9 v squared over 9 to the 1/2. I don't know why I felt like doing this first. I just did. Okay. Uh, so I just converted the integrand, but that's not what we were supposed to do. What we were supposed to do is we still need the region and we still need the Jacobian here. Okay. So um, what would we do then? So we can find the Jacobian of the transformation. At some point, we need to do that. Um, actually, no. Let's look at the region. Okay, yeah. So the curve on the boundary, oh, the curve on the edge of R, they told us was the ellipse, right? Um, oh, okay, over R, and they said that this they didn't. I didn't write it, but this curve is x squared plus 9y squared equals 1. That's the ellipse. Okay, so the curve on the edge of R is x squared plus 9y squared equals 1. Um, if we substitute in to find it in u and v, and then it's u squared plus 9. We just did this. It's the same calculation. Okay, so I just did it, so I did it quicker this time. Okay, so what that's telling me is this. So in the xy plane, which is what we started with, um, x, y, it was like this, right? And come on, just please move. Just move. Thank you. Um, you had r like this, um, right? And that was whatever we said it was, x squared plus 9y squared equals 1. But in the UV plane, it just came up this way. U squared plus v squared equals 1. That's just a circle. Okay, so that's why they suggested the integral that they did, or the substitution that they did, because that's a circle. Okay, um, so then we also need to calculate the Jacobian. We're going to need that. Um, so we have somewhere we were given x equals u, and we were also given that 3y equals v. But the first thing I did was move the 3 over, right? So y equals v over 3, right? So we don't want that form. We want the form where it's solved for x and y. That's the form that we want. So once you have it in that form, then we can compute the Jacobian. We need our partials. We need derivative of x with respect to u. That's 1. We need the derivative of x with respect to v. That's 0 because there are no v's here. We need the partial of y with respect to u. There's no u's here, so that's going to be 0. And we need the partial of y with respect to v. That's going to be 1/3. So then the Jacobian of uv, we just stick those partials in here. 1, 0, 0, 1/3. I put them in the right order this time. When you multiply this out, it's 1, 1/3 minus 0, 0. So it's simply a third. And basically what that's saying, by the way, is that it's telling you how the area changes. Like what's the area of this ellipse versus the area of this circle. Um, you have to adjust it by this factor. Okay, so we get 1/3 here. And then we can set up our integral. Again, I kind of did things out of order here a little bit. Um, so we have the double integral over s. We did figure out what it was. It's like a circle with radius 1, right? We also figured out the integrand already because I did that first for some reason. It was u squared plus v squared to the 1/2. Technically, we have the Jacobian and then the dA. So for us, that's going to be double integral over s, u squared plus v squared to the 1/2. The Jacobian was the absolute value of 1/3, which is just 1/3. And then the dA is, du dv or whatever it is. But I'll also write dA. Okay. So this is my integral where this is s. But they said we had to do it in polar coordinates. So how do you integrate over a circle with radius 1 in polar coordinates? Polare. Did it again. Polar coordinate. So they said to do it in polar coordinates. So if we're going to integrate a circle with radius 1, would be, so the way you'd integrate over that in terms of r theta, right? If you were going to do that in r theta, it would be r between 0 and 1, theta between 0 and 2 pi, right? But also, if you are going to use polar coordinates, don't we have to convert to r and theta? How to convert to r and theta? Well, basically just pretend that u and v are x and y and then do it like normal, right? Um, um, so instead of x equals r cosine theta, you'll do u equals r cosine theta. And instead of y equals r sine theta, v will be r sine theta. Okay. And then the dA, you even got to do the dA. It's going to be r cosine theta sine theta d theta. You actually have to do that again. So when we actually substitute this all in, we're going to get a double integral. R is going to go 0 to 1. Theta is going to go 0 to 2 pi. Um, u squared, oh, also u squared plus v squared would be r squared. So um, your integral here with u squared plus v squared is going to be r squared, 1/2. It's going to cancel out. The 1/3 is the 1/3. The dA is r cosine theta sine. Whoa, 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 whoa. What happened here? I have no idea what I just did when I was doing this. I have no idea. We're just doing polar coordinates. dA, it's not r whatever I wrote, right? The dA is very simply r dr d theta. I do not know what I just what happened to my brain there. Um, so when we go to write this integral out, when we get to the oops, when we get to the dA is just going to simply be r dr d theta. What was I thinking? Don't know. Okay, so this is your integral, and finally you can cancel the r squared and the 1/2, and it's just r. Well, actually, r squared to the 1/2 is r, but then there's another r. So overall, you have 1/3 r squared dr d theta. Yikes. So that was I don't know. I feel like harder than I made that harder than it needed to be, but by doing things out of order and so on. Let's make it up. Let's do a problem more according like by the book. Let's do it more by the book. Okay, that will work fine. This will be our last example because we're 2 hours. Uh, example. Um, set up the integral. They don't make us do it. Um, double integral over r 6x squared minus 12xy plus 6y squared e to the 4x plus 4y dA. Yikes. Uh, over r. Let's draw the r. So 1 0, 2 0, 0 1, 0 2. This is r. All right. So we're going to do this by the book. So rather than try to do things out of order. And then but they did give us using u equals x plus y, v equals x minus y. Okay, so this is what they said. So let's just do it by the book. So the first thing we would do is we would draw the picture. Actually, according to my rules, we sketch r already sketched. find the equations of the curves and the edge. Number 2, find your transformations. Okay, so we're already starting on step 2, where we need to find our transformations. So draw 2. Find the transformations. Okay, so they gave us this: u equals x plus y, v equals x minus y. We need it solved for x and y. So this isn't that hard, right? We will do it exactly the same way we did this once before. If I call that 1 and that 2, if I add the equations, 1 plus 2, then I'm going to get um, u equals x plus y plus v equals x minus y. You add that up, you get u plus v equals 2x, or x equals 1 half u plus 1 half v. Very similar to what we did before, right? And if you subtract 1 minus 2, then we're going to get u equals x plus y minus v equals x minus y. You get u minus v equals 2y, or y equals 1 half u minus 1 half v. Okay, so that's what we have. We have x equals 1 half u plus 1 half v, y equals 1 half u minus 1 half v. So we needed that. We need to solve the transformation for x and for y. What was the next step? 3, figure out what the limits of integration are on the UV plane. You can do that anytime. I guess we're doing it now. Um, so in order to do that, what we're going to need is we're going to need to look at this picture. Okay, so if I write the equations here, this equation right here is y equals, so first of all, the y-intercept is 2, so 2, and then the slope is negative 1. So this is 2 minus x. And the one over here is y equals 1 minus x. Okay. And then the bottom curve and the two other curves here, this curve, well, that's just y equals 0, right? And the one here, that's just x equals 0. So actually what I get for my curves are, x equals 0, y equals 0, y equals 2 minus x. But I don't like writing it this way. Remember what we did before? You should put the y and x on one side. That's actually x plus y equals 2. That's a better way to write it. And this one here, move the x over, x plus y equals 1. That's a better way to write it. Okay. So these are really annoying. They're killing me here with these problems. This is super tough. It's not super tough, but it's kind of tough. So what you have to do is, so to translate these, let me take these. curves, move them down here. So I have these curves. Okay. Now, what I want to do is I want to figure out what they are in terms of u and v. So in terms of u and v, what you have to do is replace everything with what it is. So where's my, let's look at these. Duplicate, duplicate, duplicate. Okay, I need to look at those. That's why I'm putting them there. So what you have to do is you have to say like, okay, so this is x. X is this. So if that's x, you have to replace it with u and v. 1/2 u plus 1/2 v equals 0. That's the top equation, right? The next one is y equals 0. That's this. So y equals 0 is going to be 1/2 u minus 1/2 v equals 0. Okay. Your third equation, well, that's you have x plus y and x plus y. Go back to what they said to use for your transformations, which were that you also have these for your transformations here. So don't forget these. So x plus y is actually u. So this is u equals 1, u equals 2 for the last two. So this is in terms of u and v. Okay. And so if you were going to figure out what this region looks like on the UV plane, you actually have to graph all four of these. Well, you don't really have to, but we could. So if you have like 1/2 u plus 1/2 v equals 0, that's the equation of a line. Okay. If you solve that for v, it would be 1/2 v equals negative 1/2 u, or v equals negative u. Okay. Let me just actually move this over here. So this is a curve or a line. The other one was 1/2 u minus 1/2 v equals 0. Do the same thing there. Move like you're trying to solve for v. So 1/2 u equals 1/2 v. Multiply everything by 2. You get u equals v. That's also a line. You have u equals 1. That's a line. And then you have u equals 2. That's also a line. Okay, so I'm just working with each of these. I just wanted to rewrite these to where we could look at them and see that they're just they are relatively simple. Okay, so what does that look like if you actually were to graph them? Well, here's what it looks like. So if this is u and this is v, v equals negative u is a line with slope -1. So that's like this. Okay. U equals positive v, or v equals positive u, that's a line with slope +1. Okay. Then you've got u equals 1. That is, depending on where you put 1, could be right here. And then u equals 2. Okay, so this is what the region looks like. I shouldn't call it R, I should call it like S or something. Okay, So that's really kind of an annoying line. But what this tells you then is that your region of integration, if you were trying to integrate over this, if this was an x and y, it would be easy. But because it's u and v, then it feels harder than it is just because the letters are different. But S is the set of all u and v such that so the top curve and the bottom curve, the top curve is v equals u. The bottom curve is v equals negative u. So v is between negative u and positive u. And then u, that's like your x-axis, that's between 1 and 2. And actually, you could have gotten this just from, as soon as you write this down, um, maybe you would have wanted to write this the other way around, like that. But v equals u, v equals negative u, those are your bounds for v, and these are your bounds for u. Okay, so we've done this. What's next? The Jacobian. So where's my transformations? They're here. Copy them again. So if we're doing the Jacobian x, partial x with respect to u, 1/2. Did we already do this? No. Okay. It just feels like we did, right? Xu is 1/2. Xv is 1/2. Yu is 1/2. Yv is negative 1/2. So that's different. Jacobian, actually just J. Jacobian is going to be 1/2, 1/2, 1/2, negative 1/2 equals, so you work that out, it's going to be 1/2 times negative 1/2, negative 1/4, minus positive 1/4, which is 1/2. I said 1/4, but I wrote a half. Yikes. Okay, so we find the Jacobian, 1/2. Okay, so I think now we can kind of set up our integral. Actually, that's negative 1/2, isn't it? Okay, so we know our integral over r of f of xy dA is going to be a double integral over s of f of whatever x is as a function of u and v, whatever y is as a function of u and v, and then times the absolute value of the Jacobian and then the dA. So combine all our stuff. We can do this. So first of all, limits of integration. So we found the limits of integration. U was between 1 and 2. V was between negative u and positive u. Okay. Now your function, I don't know what the function is yet, so I'm going to write it in. So f of x, what was x? X is 1/2 u plus 1/2 v. And the y component was 1/2 u minus 1/2 v, right? And then the absolute value of your Jacobian was negative 1/2, but we would need the absolute value. And then your dA is whatever the variables are. So in this case, we're doing dv du. Okay. I forgot what the function is. Let's go find the function. Did they give us a function? Oh, yes, they did give us a function. They gave us a really stupid function. I'm not going to finish this, guys. Here's what I'm going to do. I'm just going to say this was f of xy. You actually have to plug in x equals 1/2 u plus 1/2 v y equals 1 half u minus 1 half v. That is. um, I'm just going to tell you the final thing. So your final integral is u goes from 1 to 2, v goes from negative u to positive u, and if you work it out, this actually just magically becomes 3v squared e to the 4u dv du. Okay, so we did everything except actually plugging that in and simplifying. That's where I would use Wolfram Alpha. So the last thing I'm going to do is just say how to do that. Case you don't know. Come on, make small. Please just work. Please just work. Thank you. Right. So this is one of the best uses of Wolfram Alpha, in my opinion, for stuff like this. So I can just type this in. I can type in 6x squared minus 12xy plus 6y squared. Now that's a perfect square trinomial if you factor out the 6, I think, but I'm not going to, because I'm going to make the computer do it for me. So that's the, so I just type that in, and then I'm just going to say, you kind of put a comma, and then you just say x equals 1 half u. I'm just going to write it this way, u over 2 plus v over 2, comma, y equals u over 2 minus v over 2. And if this doesn't do the right thing, I know what to do to fix it, but I think it'll do the right thing. So if it doesn't, just plug it in. Okay. Okay. So you get 6e to the 4u mv squared. And the reason this is a 6 and then what I wrote was a 3 was because, don't forget, there is a 1 half on here as well that I didn't write here because that's not where it goes. Okay, so just plugging it in, that was easy on the computer, and I would do that for sure. Okay, so let me click. There's another problem that's the same, or not the same, but easier. Same but easier. I'm just clicking through to see if they ever fail to give you the x and the y, or the u and the v. So I know if I have to make another video. All right, so far what I'm seeing is they always give you x and y or u and v. But maybe the next one is different. Nope. Okay. So I believe I am done now. I hope. So yeah. Oh no, because now they say use appropriate bounds. Okay, there'll be one more video where I do that. Anyway, we're done for now because it's 2:23, so that's ridiculous. So we're done for now. I will see you later. Good luck on the homework. I really do like this section. It really is not as hard as you might think once you get started. There's just a lot of parts to everything.